This is Group 14 presenting Rome, Robotic Observer of Abandoned Materials. This was designed and developed by Daniel Clausen, who's responsible for the computer vision hardware and software, Claire Persinger, who's responsible for the PCB and hardware, Nathan Little, who's responsible for the robot guidance and web development, Ethan Robotham, who is responsible for the system integration and communication. What is Rome? Rome is an autonomous driving robot. It wanders the sidewalks in residential neighborhoods and detects trash and treasure along the sides of the sidewalk. It uploads the information of the object's classification to our website, and this allows user interaction to go find those items based off of the GPS locations that goes onto the website along with the classification. What makes Rome different from other classification models is that it uses autonomous driving LiDAR to navigate. It also uses real-time trash and treasure detection using YOLO on the Pi 5, as well as GPS tagging uploading to our website, which is at romebot.dev. And this is important, so it allows people to go find those items in real time. We also have dual processing architecture, which allows us to have Pi for our computer vision and for our ESP32S3 to have control over our system, as it is the main hub where every piece of our project is connected. This type of robot is very important for multiple reasons. One being that it supports cleaner and safer public spaces by encouraging communities to help clean up through our website's UI. It also has automated detection and reporting of these abandoned materials, meaning that while we are all out doing other things, it's able to report to us and tell us items that may need to be picked up or cleaned up. This helps cities to identify valuable or hazardous items quickly that are sitting in residential areas. It also helps reduce manual labor, as it is an autonomous robot that can act without a human behind it making decisions. And with it being live updating to our website, this allows real-time decision-making with our robot. This includes needing to ask for help from surrounding people if our robot gets stuck. It's also easily scalable to move out of residential areas and into campuses and parks. This is important because if we're able to scale it into a larger and different setting, we're able to reach more trash, more treasure, and more communities. And this demonstrates the potential of the autonomous system for a community benefit where we're all able to pick up after ourselves and connect with furniture and upcycle items that may be tossed into landfills.
The idea behind Rome is pretty simple. There's a huge amount of useful furniture and household items that get thrown away or left on sidewalks, and most of it ends up in landfills even though people in the community would happily reuse it. So, our motivation was to build a robot that can autonomously patrol neighborhoods, detect abandoned objects, and report their locations. By doing this, we're hoping to reduce waste, clean up neighborhoods, and give people a new way to find free items in their area. Along with the robot itself, we also created an interactive website where these items get posted automatically. That way, people can look up what Rome finds and decide whether they want to go pick it up. For our basic and advanced goals, the robot needs to reliably recognize the difference between treasure, meaning reusable items, and trash. It also has to autonomously follow sidewalks without drifting into grass or onto the road. Another major goal is recording and uploading the item data, including the GPS location and the classification, directly to the website. Lastly, we want the robot to be able to request human intervention through an assist mode if it reaches a situation where it can't navigate on its own. We also set some stretch goals for the future. These include adding more detailed treasure categories, improving the website so users can search by location or item type, and having the robot take and upload photos of detected items. For the basic objectives, we're aiming for at least 70% overall accuracy when classifying treasure and trash. Rome should be able to maintain on the sidewalk for at least 25 feet without human intervention. When an item is detected, Rome needs to send all data, including GPS and classification, to the website within 10 seconds. And similar to before, it should be able to request assistance using the LCD screen if it becomes stuck. For stretch objectives, we want Rome to recognize at least 3 extra treasure subtypes with roughly 80% accuracy. On the website side, our goal is to support fast search by zip code, GPS radius, or item type, with under 1 second response time. We also want Rome to capture at least 1 photo per detection and operate for 4 or more hours when supported by solar charging. Finally, Rome should be able to display its battery percentage to within about 5% accuracy.
We had a lot of goals for Rome, but the rate performance metrics really defined whether the robot was successful or not. The first one was treasure identification accuracy. Roam needed to correctly recognize what it was looking at more than 70% of the time. That level of consistency was important to show that the system wasn't just reacting randomly. The second metric is focused on navigation. How far could Roam travel without drifting off the sidewalk? Our benchmark was 25 feet of uninterrupted, stable travel. And finally, we set a requirement for the robot's detection range. Roam needed to recognize objects anywhere from half a meter out to 3 meters, a comfortable distance for most small autonomous systems. These three highlighted a clear definition of success. If Roam could identify correctly, navigate reliably, and detect objects within a useful range, then the system was doing exactly what it was designed to do.
This diagram shows how all of our hardware components connect. Starting from the power supply, a battery with a buck regulator provides a stable voltage to the system. The ESP32 acts as a central controller, handling communication with the motor driver, LCD screen, buzzer, GPS, and SIM module. The motor driver then powers and controls the two motors. For perception, the Raspberry Pi handles the data from the camera and LiDAR sensors and communicates the results back to the server. Cellular connectivity comes through the SIM module and antenna, sending GPS and other system data to the serial in real time. Each team member is responsible for different parts of the system, shown by the colored labels.
When designing the PCB, there were many peripherals that were important for us to include. The first being that our ESP32 was programmable using the CP2102 chip. We wanted to have peripherals built into the board, which is why we chose to have 3 LEDs that displayed trash, treasure, and help, as well as other signals such as booting up. We also have an LCD screen, which provides a similar function. It shows trash, treasure, and help, as well as when our robot is waiting to start moving. This PCB also takes in our 12-volt power and splits it to the different places it needs to go, such as the motor drivers and regulators. We also have pinouts coming from the ESP32 that go to our motor drivers for logic, and we have RX and TX pins that are designated for our SIM module as well as our Raspberry Pi. Additional PCB designs that we created were our regulators. This first regulator is 3.4 volts at 2 amps, and this is for our SIM module so that we're able to communicate with our website. This regulator is also designed to power our ESP32 and supply enable high for our motor drivers, as well as 3.4 volts for our LCD screen. This regulator uses the chip LM2576, which is an adjustable buck chip so that we are able to specifically have 3.4 volts, which satisfies the range of our ESP32 voltage needs as well as our SIM7600GH voltage needs. The next PCB design we came to was our regulator for 5.2 volts and 3 amps. This was to power our Raspberry Pi as well as our LiDAR. The LiDAR sources power from the Raspberry Pi, therefore this regulator needs to be powerful to do both of them at the same time. This is using the LM2679 chip, and it is again an adjustable chip because we needed to satisfy this very specific voltage range that the Pi has, which is not exactly 5 volts. Next we have the motor driver PCB design. This motor driver PCB design uses the BTS7960 chip, which allows up to 43 amps, which is beyond safe for the motors that we are using. This also has logic connecting from our ESP32 board, and it has our enable high from the ESP32 board. The design is a simple H-bridge motor driver in one direction, which is forward. And this simple design allows for a lot of troubleshooting and easy testing to be done. We also used optocouplers to isolate the board from our main power board, and those were the PC817 optocouplers.
This flowchart shows how Roam systems all interact. The camera handles classification while the LiDAR checks sidewalk safety, and both send formatted data to the ESP32, which updates the motor, buzzer, LCD, and prepares GPS data.
This slide shows the ESP32 flowchart and what the board does in our system. The ESP32 is responsible for 4 main things: controlling the motors, sending data to our website through the SIM module, parsing JSON commands from the Raspberry Pi, and driving the user interface LEDs so we can see the robot status. On Core 0, we run the motor task. We initialize the UART for the Pi, set up the motor pins and LEDs, then loop. For each JSON line from the Pi, we parse it. If it has an L value, we convert that into left and right motor speeds or stop both motors. If it has a T or G, we update the LEDs and notify the modem task. On Core 1, we run the modem task. It initializes UART2 for the SIM7600, turns on GPS and HTTP, and waits for a notification from Core 0. When trash or treasure is detected, it requests GPS data, converts it to longitude and latitude, builds a JSON body, and sends an HTTP post request to our server. So overall, the ESP32 is the bridge between the Pi, motors, and our website.
This slide walks through the full web service pipeline behind our system. Our architecture follows a lightweight end-to-end workflow optimized for real-time GPS and classification updates. First, starting at the device side. The ESP32 and SIM7600 module send GPS coordinates and classification labels, trash or treasure, directly to our server over HTTPS as very small JSON packets. These packets are intentionally small for reliability on 4G connections, and the device automatically retries if the signal is weak. We also timestamp the data at the device level for consistent event tracking. Next, once the server receives the data, it goes through a Flask backend.
Here we can see some frames
It validates
taken
the payload,
during
normalizes the label, and logs the
identification
event.
accuracy trials.
We
Keep
include
in
rate
mind
limiting
these
and
are
structured
just
logging to
frames
keep the
from
pipeline
test
stable
runs
throughout.
and don't represent overall
From there,
accuracy.
the process
There are
data
only
enters
single
our storage
instances
layer.
during the run,
We
and
store the
more
coordinates, labels, and
objects
timestamps
could have been detected
in a
during
fast
the
and lightweight
tests.
dataset, either in memory or SQLite, depending on the deployment and testing or final production. We also keep rolling a 30-minute log window and allow an admin user to reset or view the logs when needed. Finally, the front end consumes this data. The map page pulls the /map data endpoint every 10 seconds to gather updates. We use Leaflet.js with OpenStreetMap tiles to stay lightweight and free. Markers update live, and the sidebar displays the 5 newest posts with timestamps. So overall, the full flow looks like this, from device to the Flask API, then logging and storage, and then to the front-end UI, the user.
Object classification is one of the core systems operating within Roam. Object classification accuracy, maintaining at least 70%, is one of our engineering specifications. The object classification accuracy is based on data size and quality, the quality of captured frames, and how much our environment varies. Here you can see our object identification accuracy trials. Here we can see the object identification trials. There are 10 trials with varying amounts of trash and treasure. This is to ensure we stayed above a 70% accuracy at all times. After some previous failures, we focused on detecting trash accurately, and due to this, Roam improved its detection abilities. Here we can see some frames taken during the object identification accuracy trials. Keep in mind these are just frames from the test runs and don't represent overall accuracy. There are only a single instance during the run, and more objects could have been detected during the tests. Another one of our engineering specifications is being able to detect objects within a range of 0.5 meter to 3 meters. This table represents the trial we took to make sure we could always detect objects within that range. While not every object was detected, this shows that we can detect enough objects to meet that engineering specification. And here are some images from those trials. Here we can see some frames from the object identification distance test. While not every object was detected at every range, we can be sure that every object can be detected at some point within this range, and that is important for not only our accuracy, but for the functionality of Roam. The systemd service files allow for Roam's object classification, LiDAR, and UART forwarder programs to start when the Pi boots, and ensures they run in the correct order, with the UART forwarder launching first, since the other two are dependent on it. If something were to go wrong, the .service files are allowed to restart programs automatically, adding an extra layer of failsafe. Overall, the systemd service files are essential to making Roam fully autonomous and reliable.
Next, I want to walk through how we built the front-end and back-end interface for Roam, and some of the challenges that came along with it. Early on, we knew we needed a web system that was simple, reliable, and able to run on a very small cloud server, with 1 GB of RAM and 1 core CPU. So we stood up a Flask backend and paired it with a lightweight database, SQLite. That combination let us receive GPS updates quickly without overloading the machine. But even though the stack was simple, getting everything to work smoothly was not trivial. One of the biggest challenges was making the ESP32 and SIM7600 reliably communicate with the server. These modules don't always behave nicely with strict security settings, so we had to adjust the way our server handled secure connections. adjusting for the SSL certificates that IoT devices use. There was a balancing act. We still needed proper protections in place, but the system also had to accept messages from a cellular module that doesn't fully match the security expectations of a typical web client. Another hurdle came from the amount of uncertainty around the device itself. Sometimes the SIM7600 would send incomplete data or take too long to upload, and we had to decide how forgiving the server should be. If we were too strict, we risked rejecting valid packets. Too lenient, and bad data would pollute the logs. We ended up testing lots of different behaviors, basically trying to find the point where the system could stay resilient without masking real problems. We also built an internal logs page to help us diagnose these kinds of issues, and later turned that into an admin activated page. Small differences in how the device formatted its message would break things, so being able to see exactly what was arriving at the server was critical. Issues like a malformed JSON with a space, or a capital or non-capital, unexpected characters, missing fields, all showed up during testing and influenced the final design. And finally, there was the question of reliability under stress. Even though our update frequency was very low, we wanted to be confident that the system wouldn't fail apart during the demo. So we spent time intentionally breaking it, sending rapid packets, empty packets, or packets with intentionally corrupt values, just to be sure the server would keep running instead of crashing on D-Day. In short, while the technology stack is intentionally lightweight, the real challenge was making the system dependable under predictable conditions. It pushed us to make smart trade-offs and design a pipeline that could handle real-world behavior rather than just the perfect scenarios. When searching for a LiDAR, we tried to find the right price point and the application that we needed. The RP LiDAR A1 and the YD LiDAR X4 led the pack almost immediately because of their presence in the DIY community. Each coming out at $100, the YD LiDAR X4 came out a little bit on top because of its slightly higher scan rate. If we went cheaper than these options, we found that they had unstable data usually and didn't necessarily have official support. If we added the price at all, we would usually be paying for more range rather than fidelity.
The ESP32 has a lot of peripherals that need testing. I created a Pi program that simulates values that are going to be sent to the ESP32. This video shows testing for the LCD screen, LEDs for reporting trash, treasure, and when it's stopped, 2 LEDs to simulate the motors, and sending data to the website. When a T is sent, the LCD screen shows treasure and the green lights up. When a G is sent, LCD screen shows trash and a yellow light shows up. In both cases, the data gets sent to the website. When the motors are stopped, the red LED turns on and the LCD displays help. When a positive value gets sent to the ESP32, it changes the right motor value, and when a negative value gets sent, it changes the left motor. These are represented by the 2 red LEDs out in front because they both accept PWM signals.
Choosing the proper hardware for this project was crucial in the overall design, as without it, we would not have a functional design. Starting with the motors, we chose brushed DC-12 motors because they were high torque with an acceptable stall current, and additionally, they had very easy integration. Additionally, for our motor drivers, we chose to model our PCB after the BTS7960 using that chip. We chose this because it can handle up to 43 amps. It had overcurrent protection under voltage lockdown, and even though we didn't use the bidirectional use, it had that, as well as PWM speed. Overall, a pleasant choice for our design. Next, we have our battery, which we originally were going to go with 2 12-volt batteries, and we ended up just needing one 12-volt battery. The last big part of hardware that is important to review are our regulator part selections. The first being our LM2576, which is for our 3.4 volt regulator. This was chosen because it allowed us to have the correct output for our ESP32 and SIM module. We additionally have the LM2679, which also was important for our 5.2 volt regulator that supports our Pi.
The edge device we chose to use in Roam is a very important component to get right. We floated around the idea of using a Jetson for a while because we worried a Raspberry Pi 5 wouldn't be strong enough, but we ended up using the Raspberry Pi 5 in the end once we learned of the 16GB RAM version, which cleared up any concerns we had about the Raspberry Pi 5 underperforming due to the heavy load of programs running on it. The camera chosen for Roam is a very important component because it controls the quality and aspects of the frames captured that would be analyzed by the object classification software. We ended up choosing the Raspberry Pi Camera Module 3 wide version because it gave us a 100-degree horizontal field of view that would allow us to see enough of the side of the sidewalks to be able to identify objects along the side of the sidewalks, and it had a high enough quality that we could use a common everyday phone camera to capture training images without risking too much of a discrepancy between trained and captured frames, resulting in a loss of accuracy.
When searching for a LiDAR, we tried to find the right price point and the application that we needed. The RP LiDAR A1 and the YD LiDAR X4 led the pack almost immediately because of their presence in the DIY community. Each coming out at $100, the YD LiDAR X4 came out a little bit on top because of its slightly higher scan rate. If we went cheaper than these options, we found that they had unstable data usually and didn't necessarily have official support. If we added the price at all, we would usually be paying for more range rather than fidelity. The SIM 7600G-H was one component we spent a good amount of time evaluating. The main selling point was its upload speed and built-in GNSS capability. This meant cleaner GPS data without adding an extra module. The challenge was that it has a larger footprint and draws more power than the lighter alternatives. We also considered modules like the SIM 7000G, very energy efficient, but its upload speeds were far too low for the real-time mapping updates that we wanted. Then there was the JaberCat M modules like the A7670E, but they struggled with reliability, especially when handling multiple protocols at once. In the end, we chose the SIM 7600G-H because it gave us the most stable, predictable performance. It also came as a complete kit with antennas, saved us a lot of setup headaches, and the documentation was fantastic, which matters more than you'd think when you're debugging AT commands with a robot in the field.
Here's a quick comparison of the three microcontrollers we considered. The MSP432 offers ultra-low power mode, but is limited by its low clock speed and small SRAM. The Nordic, on the other hand, excels in its low power consumption and BLE support, but only has 2 UART pins. The ESP32 S3 WRoom1U, on the other hand, provides 3 UART pins, a large onboard memory with 16MB flash and 8MB PSRAM, and is backed by a massive Arduino and ESP32 IDF ecosystem. While it draws around 50 milliamps active, the trade-off is well worth it because it's well supported, has plenty of headroom, and is very cost efficient. For those reasons, we chose the ESP32 for our design. This is our bill of materials, which shows all the key components used in our system along with their costs. Major hardware items include the Raspberry Pi, the LiDAR sensor, ESP32 chip, PCB and components, as well as the chassis kit. We also included cellular communication costs, such as the antenna, SIM module, and cellular plan. Altogether, our expenses come out to about $1,273, keeping us under our budget of $1,500. Breaking it down, software costs are around $200, hardware is about $1,000, and overheads roughly $280. Overall, we made an effort to keep the design cost efficient while still meeting all of our technical goals. This is our bill of materials, which shows all the key components used in our system along with their costs. Major hardware items include the Raspberry Pi, the LiDAR sensor, ESP32 chip, PCB and components, as well as the chassis kit. We also included cellular communication costs, such as the antenna, SIM module, and cellular plan. Altogether, our expenses come out to about $1,273, keeping us under our budget of $1,500. Breaking it down, software costs are around $200, hardware is about $1,000, and overheads roughly $280. Overall, we made an effort to keep the design cost efficient while still meeting all of our technical goals.